We usually talk about 2D systems and particle simulations on the channel, but today we're taking our first steps into 3D. Can someone with zero 3D experience in Godot build an Outer Wilds style star system? I figured it'd be easy, just one more axis to work with, and in some ways it is easier. But things like camera rotations, physics collisions, and player movement can get complicated really fast. Which brings me to our overall goals for this project. I'm a big fan of games like Outer Wilds and Kerbal Space Program. And since I've done several other gravity simulations on the channel that were in 2D, I wanted to try a lightweight version of those toy star systems found in those great games. This won't be pure physics or even realistic physics, I just want it to be fun game physics. I'm using a compressed Outer Wilds style scale on purpose for this challenge. We'll have smaller planets and shorter distances to work with. That should help reduce floating point precision issues later on, and it should make gameplay more dense and interactive. Anyway, for now, we'll keep it simple and use basic spheres for the celestial bodies. We'll oversimplify things at the start to make it easier to learn about some of these 3D building blocks in Godot. For the gravity, we're going to start with numeric integration of the equations of motions for the planets. Basic time-step based integrations. But then we'll quickly change over to a hybrid analytical approach for the planets and moons, while still using Newtonian gravity with numeric integration for the player, and maybe the in-game objects later on. Before we go on, here's the technical roadmap and the pieces of Godot that I plan on using in this first video. These will probably be refactored as I go through the series, but here's the current plan. We'll go over each of these in a sec, but also keep in mind that there are some pretty big challenges ahead, and I won't get to solving them in this first episode. Implementing basic gravity effects is actually pretty easy in Godot, even in 3D, but some things, like accumulating floating point errors, moving and rotating platforms and spheres, and how the camera and player input interact during movement, those are some tough problems, especially for a wide-eyed beginner. And I just want to get the star system up and running at first, then deal with those player details later. So let's get started on the star of the show, the star system itself. First, since we're in space, let's make a skybox filled with some stars for an easy galactic background. There are a bunch of ways to do this, but I found this easy-to-use tool that can create a starry cube map for us. Unfortunately, Godot's support for cube maps is a bit awkward, and I wasn't able to figure it out. So I ended up converting the cube map into a Panorama Skybox format. I used this other neat tool I found in the official Godot documentation. I plugged that Panorama asset into the World Environment node, which is the node that Godot uses for its default environment properties for a scene, like background lighting, basic skyboxes, and post-processing effects. After assigning the sky resource material, and messing around with a few of the settings, I got a reasonable result that passes as a starry backdrop for our prototype. It's not perfect, but we can always change it later. Next up, I needed a quick way to control the camera while in the game, so I found an asset in the asset library to get that set up. I'll cover the basic player camera a little later in the video and even more in the second video. So now I have the starry galaxy backdrop. Nice. And with our basic camera script, we can look around and move around in all directions to see the stars while in the game. Next, we need to populate this 3D space with some planets and a large central star. Last year, if you asked me what a mesh was, I would have said I don't know. If you asked me today, I'd say just enough to know that I don't want to make them right now. So to keep things easy and procedural, we're going to use a technique called constructive solid geometry, or CSG for short. Godot has several nodes we can use to create some interesting 3D CSG shapes, without having to deal with building and importing fully customized meshes from a 3D tool like Blender. These CSG shapes come with some limitations and performance concerns, but they're very easy to set up for prototyping, and great for iterative level design. Later in the project, in a future video, we'll look into baking these CSG shapes into real 3D meshes for performance reasons. One of the primitive shapes you can make with CSG is a sphere, and that just happens to be the perfect shape for our celestial bodies. We'll use the CSG Combiner 3D node to form the planets and give them a little protrusion out of their north pole. With the CSG Combiner 3D, you can merge or carve out multiple CSG shapes using different operations, like adding or subtracting. So, to give our sphere some sort of visual orientation, I added a little bump at the North Pole by using a conic cylinder CSG shape and orienting it correctly just sticking out of the planet. We're using a union operation for this combiner. That's the basic add operation for a CSG. It merges the sphere and the North Pole cylinder into a single mesh that we can then turn into a collision shape for the physics engine. To add our shape to the physics engine, first, we'll use the Animatable Body 3D physics node as a container to hold the combined CSG shape. Animatable Body 3D objects behave like a static piece of the world, like a wall or a floor, but they can also be procedurally moved using code, while still affecting other bodies in the physics engine. If we look back at the CSG Combiner 3D node, we see it has an option to use collision, which automatically turns the shape into a collision object for the physics engine. That gives the CSG body a physical form. Next, because the Animatable Body 3D node is based on the Node 3D node, we can use its transform properties to move the planet around in our 3D space in all three axes. We can also scale the CSG up or down to make it whatever size we need. And we'll make a few copies of this Animatable Body 3D to create a few different planets. Let's go with 3 planets and a moon around one of the planets. Later, when the time is right, we'll turn this into its own scene. These planets will still look bland though, because we haven't added any shader materials yet. You can use Godot's preview lighting option to add basic lights while in the editor, but that won't work while in the game, so I created a temporary light source just so we can see our planets. The gray color doesn't look great. We can fix that real quick. Let's use some materials and open source shaders to dress up our simple planets and star prototypes. They'll still be sphere shapes, but we'll just add some paint on them to give a visual look. The first change we'll make is to the cones sticking out of the North Pole of the planets. We'll just color them green. This doesn't really need a shader, and we could use a standard Material 3D resource, where we set the albedo color. With that in place, the cone portion of the planets will always be green and easier to see. Now let's go over the procedural shaders. First, we'll grab this shader from godotshaders.com and make the sun. This script is from developer Oats, and I'll put the link in the video description. We'll attach the script to a shader material on the CSG sphere. After a few code changes and some color and noise parameter tuning, I got the basic sun look I wanted. I want to keep this star at the center of the world space for now, so I made sure the body's transform position was set at 0, 0, 0, which should be the default anyway. Then I made sure the CSG scale was up to 500. That may be a little small for a star, but we can always refine this later. Then we'll use this second shader I found on Reddit to add procedural patterns to our planets. This one is from Tuhinti, and I'll put that link below as well. I'll give each planet their own shader parameters and scale size, so they're easy to identify and have unique visual patterns. I already moved each planet into a position away from the star at the center, mostly along the galactic plane for now. These aren't perfect shaders, they're only meant for adding some texture to the planets, but at least the star system is starting to look like the cartoon star system I'm imagining. You'd think making a star shine light that casts shadows would be easy. Well, it kinda is using OmniLight 3D. It casts light in all directions from a single point. We'll put it at the center of the star, crank up its range, and reduce attenuation so the light reaches the whole system. We can also turn on and adjust the shadows thrown by this light. I went ahead and changed the shadows settings so they didn't look so grainy at these distances. And now our star is shining light and casting shadows onto the planets, and we'll even get eclipses from the planets and the moons. It works surprisingly well for a prototype, but I noticed the sides of the planets facing away from the star were still very dark. So, as a quick hack, I added 4 more directional light 3Ds, way out in space, all pointing inward to fake an ambient galactic glow. That worked for the most part, and now it's not so black on the dark sides. Like usual, we can adjust these, or even come up with better solutions for handling the lighting later on. Okay, now let's make it all dance. Let's make the planets rotate and orbit around the star, and a moon that orbits around one of the planets. First, let's create 3 scripts to help us. One for the global settings, one for the star, and one for the planets. In the global main scene script, we'll define gravity and timescale properties that we can adjust. We'll use these a little later for controlling the speed of the orbit animations. So now let's rotate the star and the planets. We'll give each planet a variable rotation speed. We'll use it to rotate the planet on its y-axis, each physics frame. We'll do the same for the star, but just for fun, we'll rotate it on all 3 axes. That isn't really needed, but I'm practicing and testing things out. As I was going through this, I noticed several warnings telling me not to scale or rotate the animatable body 3D directly. We'll still use its Node 3D transform to position the body in space, but we'll need to make the rotation adjustments on the child CSG combined shape inside the body node. We did the same for scale earlier. Now that the planets are rotating around their North Pole axis, we'll use Newton's laws to calculate the gravity forces of all the planets to actually move them around in space. Good old n-body gravity. During each physics time step, we'll use our custom timescale, the delta time from the frame, and some new values from each celestial body to calculate and apply Newtonian gravity that acts on each object. We'll give each planet and the star a variable to hold their mass. For the planets, we'll also add a velocity variable telling us what direction and how fast the body is moving. We'll need to set this vector for each planet to give them their starting orbital paths. Now we can apply the gravity calculations for each of the planets and move them using basic velocity-first Euler integration method. Assuming our starting velocity calculations are correct, when we run the game, we should see the objects moving around the sun. This is one of my favorite, easy-to-implement mechanics in space simulations. It's so satisfying. But with this many bodies and at this compact scale, this method falls apart pretty quickly, even if we could get it almost perfect. And even then, it's bound to grow more chaotic as time ticks forward. And I didn't even get close to getting it right. Making stable n-body simulations is hard, if not impossible, especially at this scale. So let's make an executive decision to use Keplerian orbital elements for the star system bodies. This way we can always calculate the exact position of any body by simply using the exact point in time that we want to know about. It's deterministic in that it should play out the same way every time. It's not exactly how Outer Wilds does it, but this analytical approach solves a whole bunch of problems, especially with using floating point numeric integration that accumulates over time. From what I've read, Outer Wilds doesn't actually do n-body gravity between the planets. The planets don't affect each other in that game, even though they are affected by their parent object's gravity. I haven't really tested that myself, but we're essentially going to do the same in our 3D prototype, just taking it a step further. Crucially, this will let us make some unrealistic orbits for gameplay and level design reasons. It'll reduce the n-body problem to a nested set of solvable two-body problems. Each body only cares about its parent, so we won't need to rework a bunch of things whenever we decide to move and adjust the planets later on. You can check some of our older videos on the channel for more information on using orbital elements and state vectors in Godot in 2D. This time I had to use all of the elements to get the full effects of the 3D orbital paths, but the gist is the same. Here are the orbital elements that we'll add to each planet. Now, the star system will be organized as a hierarchy, using an exported parent body property on each planet, where each celestial body except the star is assigned to its parent body. In the case of the planets, their parent is the star, and for a moon, its parent will be one of the planets. Now we can determine each planet's motion by solving the Kepler equation. None of these planets or the star actually affect each other gravitationally. Each orbit is solved as a simple two-body problem relative to its parent, so they're effectively moving on rails. That might sound unrealistic, and it is, but it doesn't mean that our player character and the other in-game objects can't behave differently when we finally get to the player controls. And we'll still get that sense of harmonic motion you might expect from the large orbiting bodies in a space game. To help visualize and better see these orbits, let's draw the orbital paths directly in the game. These Kepler orbits and their elliptical shapes can be described with the Keplerian orbital elements. In 3D, you might use a custom mesh to draw this, but I decided to try my luck at using the Mesh Instance 3D node and an immediate mesh to create a procedurally generated ellipse directly in the game. And it works surprisingly well, even though it has some limitations. First, we'll create a Mesh Instance 3D for each body and place them all into a single container node. We'll make each instance use an immediate mesh, and give them a simple spatial fragment shader to set the color for the lines. Now we'll create a script called KepOrbitGD, and attach it to each mesh. This will give the orbits a single property, where we can tell it which of the planets or moon it should calculate and place. It uses a line strip surface to manually draw an ellipse, using a set of straight lines. All I needed to do was grab the orbital elements, calculate the exact shape and orientation of the ellipse, and move it to the correct focal point at the parent body. After a few attempts, I had it working. And thanks to viewer comments, I already know that this can look wrong when zoomed in, especially for larger orbits or with highly elliptical orbits. It's something I'll need to address later on. So now I can see the orbital paths in the game, but since this was an immediate mesh, we won't get to see it in the editor. To get around that, I converted the scripts for the orbits and the planets into tool scripts, which are both a blessing and a curse. After reloading the scene, I could now see the orbits directly in the editor. I could even adjust the orbit parameters and see the orbits and the bodies update in real time, all without having to start the game. That's really cool. But I also wanted a way to override the orbit animations, so that the planets could be viewed at their official starting point to make it easier on a developer. So I added this checkbox as an extra parameter. When it's checked, the planets won't move in space in the editor based on time. They'll still rotate though, so I'll have to fix that later. Anyway, now we can move the planets and visualize their orbits over time, both in-game and in the editor. Next, let's give everything some real mass and add the gravity fan physics for the player to experience. Oh wait, we can't have a space game without adding a telemetry panel, if only to print out some key information that we want to see while adding and testing features. Since we're in 3D, we can't just print 2D labels to the screen like we're used to. Instead, we'll draw the 2D information to a subviewport and use a subviewport container to draw it. We've used this technique in previous videos to draw on secondary 2D screens. This will work the same way. It'll overlay on top of our actual 3D game scene, with the subviewport configured to use a transparent background. Now we can add whatever UI buttons, toggles, and switches we want here. I just went with a simple multi-line label for printing data points. We'll use it to show the planet's position, and later on we'll show the player's position, velocity, and relative velocities to the main celestial bodies. And in a future video, we'll look at adding a better HUD readout for the player. Right, back to the player gravity and controls. Our camera so far was based on a free-look camera asset that emulates the 3D input controls used in the Godot scene editor. You can find that simple free-look camera on the GodotEngine.org asset library. It works great since you kind of develop a muscle memory when moving the mouse around in the 3D editor. But we'll definitely want more gamey controls to make a fun controllable character for the player. Especially because we want the small object in the star system, like the player and their ship, to be affected by the local gravity from the planets and the star. So let's start with a CharacterBody3D node, and put the camera inside of it for now. This will be our player object. And we'll give it a player script. It'll also have a small box collider, and use the move and slide function to fly around space. In a moment, we'll morph the free-look camera logic into a 6 degrees of freedom player controller, and remove that old camera script. Before we get to that though, while writing this, I found myself constantly having to move the player starting position by hand in the editor, and it became pretty tedious. So let's also add a set of node 3Ds so we can use it to tell the player where they should start when the game begins. This is a great way to have a bunch of starting point presets to choose from. Okay, for the player's input, we'll start simple. We'll handle it in the same way that the old camera script does it, using the input function. But we'll also add and remove some features. We'll add new buttons for rolling the player, and change the existing buttons to have these controls. For the gravity physics, it's pretty easy to give the player some mass, and we'll use that mass and the mass from all of the large bodies to calculate the force of gravity acting on the player. We combine that gravity with the player's inputs to get their change in velocity for the current frame. In theory, this lets the player experience gravity as their velocity is constantly being nudged towards the center of the forces. And here's where some of the challenges started to get real for me. We're using some parts of Godot that aren't very clear on how they're supposed to work, at least without digging deeper into the actual engine source, which is probably worth a look sometime. And being so new to the 3D concepts, there wasn't a quick solution other than to just try things out and see how they work. For example, for the planets, I'm using CSG with collisions turned on. The doc says it creates a collider that acts like a static body, but static bodies aren't really meant to be moved around. So instead, I went with an animatable body 3D node as the parent and put the CSG inside that container. And that seems to work in that the static collider from the CSG is being moved around with the planet's orbits and spin. Good enough for a prototype, I suppose. Then there's the in-game player character. It's a CharacterBody3D node. This means we have to move the player ourselves, and we can't rely on the built-in physics in Godot. The physics engine won't move it for us because the node's designed to only move based on code and the player's inputs, not from physics interactions. We've been using Move and Slide while flying in space, and it works great. It even handles basic collisions, but on the surface of a planet, this seems to be a tricky choice, or we'll need to handle it with extreme care. It definitely doesn't play well with the 6 degrees of freedom controls and the moving static colliders as they are now. To expand on this problem, let's look at 3 examples. In the simplest case, imagine a static sphere planet with the player standing still anywhere on its surface. We could always assume up is pointing away from the center of this imaginary planet. We could try changing our character's up direction and maybe solve some of the camera problems that will undoubtedly show up. But even before we get to fixing the camera and the idea of which direction is up, there's another complication to look at. Our planets aren't really static spheres. They're both moving and rotating, moving along their orbital paths around the star and spinning on an axis. And that means our character is not just going to simply land on a planet. It will still collide because we're using Move and Slide, but then it'll just be slid along the planet as it's pushed out of the way. That's not ideal. Now, think about that same static planet, but this time it's spinning in place with the player on the equator. We'll assume the player isn't entering any movement input, and that there's gravity that points to the planet's center so we can fake the pull of the planet. In theory, this means that we need to add the planet's angular velocity to the player's motion, based on where they are on the surface, even though the player isn't entering any input commands. Finally, let's pretend our imaginary planet starts moving in an orbit while it's already spinning, with the player still on the equator. Now we'd need to also account for the planet's linear velocity, not just its rotation. So the player isn't just moving on their own, they're effectively riding on top of a moving, rotating reference frame. Right now, the player just gets pushed out of the way by the planet's collision shape. It won't stick to the surface, and it definitely won't inherit any of the planet's motion. The problem is, none of this is actually implemented out of the box, because the engine doesn't handle this for you with a CharacterBody3D. You have to build and code the movement yourself. I even considered going directly with a RigidBody3D controller, which would be fully affected by the physics engine. But that just makes certain things easier while making other things much harder, like having to move the objects with real physics force integrations. That might still be a solution we look further into later on, though. Or maybe we'll need to try a custom move and collide loop instead of using Move and Slide. Or even a hybrid controller that tracks control states like grounded, flying, and in-space controls, and handling everything with relative forces instead of global forces. I'm also thinking about moving the world origin to focus on the player instead of the central star. We'll see how that goes to help reduce some of the precision issues we might run into down the road. Anyway, that's as far as we're going to get in this first video. We have an animated star system working in 3D with collision shapes, and the start of a character controller letting us fly around the system with the camera. In the next video, we'll improve the character controls and work on some of these camera and collision challenges. If you have suggestions, advice, or just want to chat, don't forget to leave a comment. Thanks for watching the Pathfinder's Codex, and never stop trying new things.